Welcome back. Today we're going to get a little bit more serious about circuits by introducing the idea of current. And by introducing the idea of current, not only are we going to be able to do more with circuits, but we're also going to start relaxing one of the most important assumptions that we've made in this class up to this point. Namely, we're going to allow things to actually move. And that's going to have a huge effect on what happens when we talk about electricity. So let's talk about movement. If I take a conductor, which is of course just a material that has charges in it, in this case we're going to allow both positive and negative charges to be in it. We have charges inside a conductor, but what makes a conductor special is that these charges are allowed to flow. They're allowed to move. And so when I apply an external electric field to this conductor, I end up with positive charges moving with the electric field lines and negative charges moving against the electric field lines. If I wait a given amount of time then, I expect that all of the negative charges are going to actually be pushed as far as they can possibly go in one direction, and all of the positive charges will be pushed as far as they can go in the other direction. And this is an interesting situation because as these charges accumulate on the top and the bottom of this particular piece of conductor, what's going to end up happening is that these two rows of charges, or these two surfaces of charges, are going to act sort of like a capacitor themselves, and they're going to create an electric field, which I'll call E2, which is necessarily pointing in the opposite direction to the original field. In fact, what happens is if this E2 isn't bigger, or isn't the same magnitude as E1, then E1 is still going to allow charges to move until such a time happens when the magnitude of E2 is exactly equal to E1. And so in statics, what we find is that if I have a piece of conductor that's in an external electric field, all of the electric fields inside that conductor, the external ones plus the internal ones, are going to always cancel out to be identically zero. And this is really the definition of a conductor. In a static situation, charges will always build up on the surface of a conductor so that the electric field inside is zero. Now, this is a question I love to ask, and I won't overstate it here. The electric field inside a conductor in a static situation is always equal to zero. And in fact, because all of the charges align up on the outside, on the very surface of the conductor, this leads to an effect that's known as the skin effect. And there are lots of great demos for that, and I encourage you to look them up on the YouTube. But another interesting thing can happen in this situation. If I have all of my positive charges lined up on the top of the conductor and all of my negative charges lined up on the bottom, these charges are still being pushed outward, right? They're still being pushed by the external electric field. And so if I provide them a situation where there's another path, then what can happen is that these charges can actually flow along the outside of this circuit, and they can then go back into the conductor from the other end. And when that happens, I end up watching a perpetual situation where the positive charges are flowing around this circuit in one direction, and the negative charges are flowing around this circuit in another direction. And although this can reach a state of equilibrium, it's always dynamic in that the charges are always flowing around the circuit, and there's nothing I can do about it. So now I can define the current, which we label as I, as the derivative of the charge with respect to time. That is, if I have some wire with some cross-sectional area, I can measure how much charge passes by that cross-sectional area in a given amount of time, and that's the current I. Of course, if I've defined this cross-sectional area, I can also ask myself, well, what is the density of that current? So there's another quantity that's known as the current density, which we call little j, and that's defined to be the current divided by the cross-sectional area. So this is a measure really of how much current is there passing through a surface per given unit volume, per given unit area of that surface. And of course, if I want to combine these two, I can always say that the total current is of course just the integral of the current density over the surface, and again, my surface here is always going to be defined to be the perpendicular normal to that surface. And I have to dot the two so that I really calculate how much current is going through that surface. And of course, this is going to remind you of that quantity that we know as flux. Okay, so once I have my definitions of current and current density, I might want to go a little bit further and actually talk about what's going on in the problem. Okay, so now let's set up a physical situation. I have a wire, and inside that wire, I apply an electric field, which is going to be pointing to the right. Now, if there were positive charge carriers in this situation, those charge carriers would move in the direction of the electric field, and they would also move to the right. But of course, you know, because you've heard this story 2 or 3 times in your life, that the charge carriers inside a wire that move are not positively charged, but they're negatively charged. They're actually electrons. And those electrons are going to move to the left, right? They move in the opposite direction of the electric field lines. But that doesn't stop us from defining the current to also point to the right, right? So the electric field and the current are pointing to the right, but the actual negative charge carriers are pointing to the left. We're going to say that those charge carriers propagate through the wire with some speed, which I'm going to call v sub d, which is shorthand for the drift velocity. That drift velocity is going to represent sort of the average speed per charge carrier. So if I'm watching this wire now for some delta t, I can actually calculate the total amount of charge, which in this situation is kind of given by this section of the wire, the total amount of charge that's going to cross some cross-sectional area A in some time delta t is going to be all of those electrons that are pushed through that surface area at some given time, which is going to tell me that the length of the wire that's important to us here is given by the drift velocity times the time, right? So that whole distance of electrons is going to pass through the cross-sectional area in delta t. Okay, so I know that my current density J is going to be the amount of charge per unit area per unit time. Of course, my charges here are actually electrons, and so I can say, well, my charge is going to be broken up into the charge of the electron times the number of electrons times the volume of electrons that pass through that surface, that's A times L, again, divided by the cross-section area and the time it takes to move. But of course, L and delta t combine to give me this drift velocity, and so the actual expression for the current density related to the quantities of real interest. The current density is the velocity of the electrons, or the drift velocity of the electrons, times how many electrons there are, right? So the velocity of one times the number of electrons is going to give me the total charge that's passing through that surface area in a given amount of time. Using again that expression that tells me that delta t is equal to L over the drift velocity, I can convert this now to a vector, which also says that the current, sign is going to be in the opposite direction to the drift velocity because the sign of the charges that are moving is less than 0, so the charges are negative. And now you say to yourself, well, this is interesting. I see that my current is oppositely directed to the drift velocity, and you start to think, oh, well, maybe this comes from the fact that the force on my charges is also oppositely directed to the electric field, right? This is true because I have negatively charged objects, and therefore they're being pushed in the opposite direction. But I can't go so far as to say this velocity comes from that force, right? Because after all, if I were applying a constant force on my electrons, they wouldn't be going with a constant velocity. They would be accelerating, right? So there's something else happening inside the wire that's causing these electrons to move with some effective velocity, right? The drift velocity here is an effective description of how the electrons are moving through the wire. You can kind of think of it as a terminal velocity in the sense that there are other forces in the wire that are interacting with the electrons and causing it to slow down. But again, that's also not a great example because some of the electrons as they're moving through the wire might get stopped, right? So it's not necessarily a measure of the actual electrons as much as it is a measure of the electrons. Sort of as an effective description, sort of the fluid of electrons that are moving through the wire is really what's being described by this equation. At the same time, though, I can go so far as to say that the current density J is going to be proportional to the direction of the electric field, right? So this terminal velocity is in the direction of the external force, which is given by the electric force, which is derived from the electric field. And so we can say that that the current density vector is going to be in the direction of the electric field. But we actually have to measure what that direction is using some effective constant, which we're going to call sigma. And that sigma has a name. It's called the conductivity, because the bigger sigma is, the bigger the current density is that corresponds to a given external electric field, right? And so the conductivity tells us that how well the material responds to the presence of an external electric field. Because we like to play games with these constants, the conductivity sigma is related to the resistivity rho, where rho is 1 over sigma, and the resistivity then goes down as the conductivity goes up. And so the smaller the conductivity is, the less likely it is for the less current I get for the same external field. Therefore, somehow the material is resisting the flow of electrons more, and that's where it gets this name, the resistivity. So now if I go to magnitudes, yes, and I should mention, yes, this is a sigma and a rho. No, they don't have anything to do with charge and current densities. We're just running out of letters again, right? But if I now go to magnitudes, I can solve for the resistivity and see that the resistivity is just the magnitude of the electric field divided by the current density. I can do a little bit more algebra with this because, of course, the electric field is just the change in potential divided by the length of whatever wire it is that I'm looking at. The magnitude of the current density is the magnitude of the current divided by the cross-sectional area. And so I end up being able to relate the change in potential is equal to L over A times rho times the current. And now when I write it this way, what I see is that there's a relationship between the total change in potential across whatever length of wire or whatever length of conductor I have, and the total amount of charge that's moving through that wire. And so that relationship, if I make the potential difference bigger, I get more current. If I see a bigger current, that means I must have a bigger potential difference. And there's this constant of proportionality, which is L over A times rho. And that constant of proportionality is the thing that we call the resistance. And so if I look at it from the point of view of measuring what is the change in potential, well, it's the resistance times the current. If I look at it as a function of the more external change in potential I apply, that is, the bigger the battery I hook up, therefore the larger the electric field, can I see a difference in the current that's produced? Well, if my material obeys this equation, that is, if the relationship between delta V and I is linear, then I see a nice line on this plot that tells me that the current gets bigger as the change in potential gets bigger. And if the material acts like this, then it's said to obey Ohm's law. And in fact, the statement that delta V is equal to Ri is Ohm's law itself. That is, the bigger the potential difference, the bigger the current. I don't want to leave you, though, thinking that this is some real law in the sense that materials have to obey this. It turns out that this is one of these laws that we see because lots of materials tend to obey this. And in lab, you'll measure lots of materials where the relationship between the current and the change in potential is linear. But there are lots of materials for which it's quadratic, or they have other funny shapes that the current really non-trivially depends on the change of potential. And therefore, I want you to think about Ohm's law as being a great description of the relationship between potential difference and current when it applies. Okay? And generally, if it applies to a situation, we call the material that is in that situation a resistor or a pure resistor. Okay, so here are your take-home points. When I think about charges flowing through a wire, I want to think about the drift velocity as sort of a terminal velocity for an effective charge, not the velocity of any given electron. If I have a normal material that's responding well to what's happening with an externally applied electric field, then I can calculate the resistance, which is a function of the resistivity and the length and the cross-sectional area of the material that I'm looking at. And if I have a material that obeys Ohm's law, then I can write down Ohm's law, which tells me that the change in potential is proportional to the current. And again, that only applies if it applies.